In the second part of section 8.5, we're going to talk about exceptions to the rule when it comes to electron configurations and how to write the electron configurations for ions. Let's begin. As you move further away from the nucleus, the subshell energies begin to overlap, as discussed in part 1 of this lecture. This overlap makes it easier for electrons to move between sublevels, and as a result, electrons will sometimes deviate from their expected electron configuration in order to achieve a completely filled or half-filled outer energy level. The most likely culprits are the D block elements in the 4th and 9th columns and the F block elements in the 6th and 13th columns. Let's look at some D block examples. We expect chromium to have an electron configuration ending in 4s2 3d4, but if we slide one of the 4s electrons over to the 3d subshell, we achieve two half-filled subshells, which is lower in energy and what is observed. Copper does the same trick, but this time borrows a 4s electron to complete the 3d subshell, which increases the stability of the atom. In general, we see that when an element has a configuration that is one electron away from having a half-filled or filled D subshell, then an S electron will move to achieve that lower energy configuration. Now, to make bonding happen, we need to talk about how to form ions using our electron configurations. If we need a negative ion, we add electrons. If we need a positive ion, we remove electrons. The goal of an element is to achieve a noble gas electron configuration. When doing so, sometimes we end up with atoms and ions that have matching electron configurations. We classify these atoms and ions as being isoelectronic. Let's work through a couple of examples to explore this concept. Let's determine the number of valence electrons for sodium and fluorine. If we look at sodium, its electron configuration is 1s2, 2s2, 2p6, 3s1, which we could rewrite as having a neon noble gas core and 3s1. If we examine fluorine, its electron configuration is 1s2, 2s2, 2p5, which we could rewrite as having a helium noble gas core, 2s2, 2p5, but it doesn't really save us much writing. Either by counting the columns for these main group elements or by using the noble gas core notation method, we see that sodium has 1 valence electron and fluorine has 7. Hold on to that information for the next slide. Using the electron configurations we just wrote, modify them to represent the electron configuration for the fluoride anion, F-, and the sodium cation, Na+. Fluorine needs to gain an electron to become the fluoride anion, giving us a 1s2, 2s2, 2p6 configuration. Sodium needs to lose an electron to become Na+, and gives us the same electron configuration. We see that a neutral atom of neon also has this electron configuration, so we can say that F-, Na+, and neon are isoelectronic. Transition metals, meaning those metals found in the D block of the periodic table, will lose electrons from the outermost energy level first, which is typically the Ns level. Take zinc, for example. To form the 2+ ion, it easily loses the two 4s electrons, even though the 3d electrons were the last electrons we added when writing out the configuration. This is pretty typical for our transition metals. If we need to remove more than 2 electrons, only then will we remove the lower energy d orbital electrons. Let's look at another example where we can apply this concept. If we write the electron configuration for a neutral atom of iron, we get argon 4s2 3d6. If we need an iron 2 ion, we remove the two 4s electrons first to get argon 3d6. Iron 3 requires us to remove 3 electrons from the neutral atom, so we get argon 3d5. Please spend some time working through more questions like this in the textbook. As always, here are some parting thoughts from the authors.